Okay, so we will start. Yes, so today our topic is about word embeddings, so vector some representations of the text. And you already had a lecture about this topic. I will give you a short reminder about the motivation of this task. So when we are dealing with text, of course, we have some string variable, and unfortunately, the models in data science don't work with strings, they work with some numbers. And in this way here, that's why we need to somehow um, represent our text in some numerical way. Of course, there are different approaches for this. And when we first think about this, for example, we can have some vocabulary in the whole language, in English or in Russian, and just enumerate all the words, for example. You can pick up the word and then calculate the index of this word, and this will be also a numerical representation for the text. Unfortunately, this approach will not give us a lot of information about the word and about its meaning, and maybe for the further model it won't work well. During all this time, during after the popularity of deploying, there exists a lot of models for this, and you already, I believe, heard about BERT and Elmo. Today, we will look at some classical, we will go to the roots and we'll look at some classical models. And firstly, we will start with account-based models. Again, you have already saw this picture. What we want to do. So one of the more advanced representation after the just indexing the words in the whole vocabulary is to calculate some popularity of the words in the text, not even in the text, but in the whole collection of text. And what we want to approximate here, we want to calculate the number of words of some particular word in the text, and we want somehow to weight this number because, for example, if we're talking about prepositions, the amount of the prepositions in text is very big, but unfortunately, this is not a very sensitive words that will give you us a lot of sense. And on the other hand, some really meaningful words can be very rare in the text as well. So we want to weight again this number with some term that will give us this meaning that when the word is too popular in the collection, that we do not want to count on it too much, but when it is rare, we want to give it more meaning. And I believe you know that I'm leading to the TF-EDF approach, and to represent this approach, we will solve some task. We will have a data set of product reviews, and we want to find the most similar review from this data set. So uh, it is also a very classical problem. We want to build some recommendation system. It can be like that, some retrieval system. So when we will give a text to the model, and we want to retrieve some similar text to this request. So let's start. Firstly, we will download the data. So as it was said, it is the data set with reviews. And here we have some imports and data set. So we will have a glance of it. So the amount of reviews here is 23,000. And we have here such columns as some additional closing IDs, age, title, review text, and also ratings, and etc. Today we will focus only on this column, on review text. We will use it for our trivial task. And so let's go further. As you also should remember from the previous seminar, you have already was introduced with pre-processing of the text. And today here we will have some small task about it. Again, we will have just some raw text where people can write a lot of smiles, a lot of punctuations, maybe some mistakes in the text, and we want um, to clear text and to form words in their initial form. Here you already have some predefined lemmatizer, tokenizer, and also you here have the list of stop words from English. And your task is to complete this function that will return clean text. And I will have also a hint for you that the text, the new tokens should be joined with space. I believe I can give you maybe 7 minutes. So you can write me in the chat your ideas, what we need to do. I will complete it with you also. So I suppose that everybody just thinking about the task or preloading the document and loading the information. Okay, to be your radio voice in this task, so what should be the steps here? Here you have a document, and again, this is a string. What we need to do for the first step, we just need to lowercase the document. It can be done with one simple function. After that, we need to tokenize the text. So we have some string, yes. So we need to extract words from the string, and that can be done in several steps. You can just split the text with just space, but unfortunately, this is not the best way to do because we have some punctuation. For example, we have dots in the end of the sentences, and it is not divided with from the word with the space. And that's why you have here tokenizer that will help you to tokenize the sentence, and not only with just spaces, but also with some punctuation. After that, we should remove stop words. As you remember, stop words is some not essential words in the text. For example, it can be again some prepositions. Also, there can be some very popular words, for example, like very interesting, that can be faced in the text, in a lot of text, and that they don't bring a lot of information with them. And after that, we need again to get words in the initial form. So we need to extract lemmas. I believe that everybody remember what is lemmas. It is one of the initial forms of the. So you can extract stems or you can extract lemmas. So lemma will bring you the initial form again from the word. So the difference is that you can just divide the ending of the word, but you can really get the initial form. And after that, you will have the list of tokens, and you just need to join them with space. I still waiting for some hints from the chart. I see that there is no document law. Yes, it is. This is the first solution here, or in the chat. You can write in your notebook, and you can just copy paste in the chat, so I can see. Yes, so I can see that you are doing something and you are doing it correctly. So for the first step, yes, we will have here a document. Oops, sorry. Yes, Actually, the both answers are correct. After that, I will just do it step by step. So I will not do it in the one line to just to have clear code. After that, we will get yes, words or tokens, and we will tokenize the text with a tokenizer. Nice. Removing stop words. And lemmatizing. I will provide you a more advanced example. So here we will, yes, so the answer was correct as well. Here I will show you that we can lemmatize not the whole set of words, but also words from some specific part of speeches. Just to show you an example. Again, this is can be done not to deal with some auxiliary words and to work just with more useful words. And as usual, those are nouns, verbs, adjectives, and adverbs. And lematizer. And here you also put not only the word, but also the part of speeches, the part of speech to make lemmatization more accurate. And here just join with space. Yeah. Is there any questions? Maybe I should wait to complete if you want to complete your code and run it as well.
Is there a way not to iterate over all part of speeches in the last few strings? So just like to write for pause in and like wordnet pauses, or we have to write them manually every time?
Not you. You shouldn't write it every time. So if you look in the chat, there is an answer without any usage of part of speeches. But here as example, I iterate, not iterate, but I here wrote it explicitly because I want to just use this exactly part of speeches. But you can not pay attention to this, and you can just use all words from your text and lemmatize them.
Oh, okay, thank you.
I think the question was that whether we can avoid writing this loop, rather making it inside using some condition or.
No, it was about
Okay.
writing all the parts of speeches, noun, verb, etc.
So I have answered the question, yeah?
Yep, thank
Yeah,
you.
okay. Yes. After that, we have just some cleaning of the data set. We will use, so as you remembered, we have a pretty big data set. Oh, actually, also I have some advice for you before we haven't gone too far away from the beginning. As you know, I will just remind you. So if you want to use GPU, that we will have, no, I don't want to use that. So if you want to run in the collab, and we will need GPU for some examples. You can change your runtime type, and for the initial, I believe that in Galapa you have nothing for here, and you can change it for GPU or TPU. If you haven't done this yet, you should do this. And after that, you should run yourselves because the runtime will be restarted. I can wait again for some minutes. It will not take you a lot of time, but actually you should do this. Sorry for that. In that time, I can answer some questions. Why exactly them? Them, you are talking about the part of speeches that were, yes. Just because if we're talking about the structure of sentences, actually you have some object, you have some subject, you have some verb, and in the majority of cases, this is nouns and verbs. Also and can be as additional information, adverbs and adjectives. So this is like the most meaningful part of speeches as usual in the text. Because again, if we're talking about some prepositions, they are not so meaningful, and they can bring some noise for our model. And we want only to work with the most meaningful words in our text. Yeah, does it work for you? Yes, no? I expect silence, yes.
Yeah, I guess the question like why exactly we select these four parts of speeches, but yeah, it's really depends on the task and as any pre-processing. So for the task of retrieval, this pre-processing is kind of standard to remove the stop words and to select only meaningful part of speeches because of this specificity of TF-IDF schemas that might not hold for other models which, let's say, take into consideration the sequences of all words like RNNs. And yeah, so for this model, empirically, it was found that it makes sense to get rid of this, and because of this bag of word assumption, it helps. But yeah, for other tasks, it might be a different part of speeches you might want to get rid of. For instance, if you do some authorship attribution, what you really care about is how people use determiners and punctuation, and actually you don't care too much about nouns and verbs and content words. So it might really be very different factor.
Yeah, thank you, Alexander. Next, we will again just preprocess our data set, and as you remember, we have here 23,000 overviews, and we will choose only some subset of them to make our model quicker. Just for example, after that we also delete some non-samples and pre-process our text. So this cell is only for this. Yes. So you can see the new data set. We work with review text column, and here we'll have process review. I here also wrote for you some example of some pretty fine output for the text comparison. For example, in Python, you can use HTML to build some pretty tables and other clickable stuff. And here, just to compare the results, we will have a two-column table to compare our original text and preprocessed text. And so if we look at the text more carefully, you can see that firstly, it is much shorter than the original text, yes. And this is because we delete some unuseful words, we delete stop words, we work only with some set of part of speeches. And also we can look at the words if they have changed or not. So knee dress, comfortable, still the same, like various. So for example, the word colors and the word color. We can see that was the very simple lemmatization, but we here have the word now in its initial form. Used, use, stripe, and etc. You can try any different example from here if you want to compare more. Yes. Okay. So Now we have the new data set with two columns with review text and with the process review. And we will basically, of course, work with this set of documents with our process reviews. And what we are going to do next. Next, we are going to implement TF-IDF approach for the text vectorization. And here you have a small reminder about what is TF-IDF. As we talked about it in the beginning, we want to somehow estimate the popularity of the word in the collection of the documents. The first term of so what are these letters stand for? Yes, TF-IDF. This is turned frequency and inverse document frequency. What is the meaning of that? So the first part of the product is TF, term frequency, of the term in the document. So this is just the popularity of the word in the document. So this is just the number of times this word is represented in the document. IDF, inverse document frequency. Again, so we want to to keep the more sense of the words, the more sensible words. When we have some preposition, it can be very popular in the text, in the collection of the documents. But unfortunately, it doesn't bring too much sense. On the other hand, rare words can be represented only in one document, and that means that these words are very important for this document. And as it is written here, we divide the number of the documents in the whole collection to the number of the documents where the term T is represented. And in that way, we will achieve our inverse document frequency. We also use log just to scale this number and not to work with zeros. And logarithm can be with any base. I can maybe make a pause to if there are any questions, because further we will use all this knowledge to write our code and to implement TF-IDF with our own hands. Maybe there will be questions further, because again, the first part of the task is to calculate the document frequency of the term in the collection of the documents. So here you have the hint that we want to save in the structure. So this is a dict, and we want to save here the information for every token. So the keys of this dict are tokens, and we want to store the values as a number of documents where this token occurs. And we will use this structure further. Again, I will wait for your guesses. What should be written here? Okay, so maybe I will slowly start to write. So again, what we want to store, we want to store our tokens and corresponding number of documents from the collection where this token occurs. We will go through the data sets. And so what we have here, yes, I can see some answer here in the chat. Yeah, okay, so for the first answer from the Mikhail, yes, actually, yes, this is correct. And I also like that you use this try except trick. I will also use it as well. And for the answer from Artyom, yeah, I also believe that this is the answer. I will use okay my prepared answer, but yours are correct as well. For others, okay, so we will work with process review column, and as you remember, we join tokens with space, so we can just now use not tokenizer but just split with a space and get the list of tokens. And after that, yes, we just go in the loop, and if there is such key in the dict, then we just increase it. On the other hand, we will create new item. Process.
Yeah, I guess it also makes sense to clarify like the differences potentially between solutions of Artem and Mikhail. That yeah, if we work in Python, Python is a dynamic language. So yeah, for clarity, if you use loops is better, but some built-in functions might be faster, like the one like sum and things like that. So sometimes if you use more like functional approach, it's less readable. But in this seminar especially, we try to strive for clarity, not optimize things. But yeah, if you observe that you need more performance, you might want to just use these built-in functions, because pandas and other packages like this, they basically written in Python, which means that they much faster than just a native Python loop.
Yeah, okay, so yeah, so that's why we'll have here for other people just some row by row, step by step done solution. And we will go further. I believe that everybody got the solution, and we will just look at the number of tokens that we have. It is 2015. 98, just 9, just to obtain this information, and we will also store the total vocabulary of the collection. So this will be just the keys of our dictionary, because here we store keys as our tokens. After that, just a simple function to Return the processed value for the number of documents that we have already calculated. I will not wait here for a very long time because it's pretty simple. Yes, maybe to make your life easier. So as we have already calculated everything to obtain this result, we will just return the value from the dict. And on the other hand, we'll remain the number as 0. Yes. Yeah, okay. I will wait for some seconds for you to write a code. Because after that, we have the very important step. We want to calculate TF IDF for all our tokens. Here we have some helpful structure from Python. This is counter, and I also here have for you the example of usage of this structure. And with the counter, you can easily calculate the number of accuracies of the token in the text. And actually, it's also of some item in some list, because here we need to process text as a list, so to split it for the tokens, and after that you can calculate the number of this token occurs in this text. And so the main part, TF IDF, we already have calculated the number of documents in which the token occurs. And now we can use this information to obtain the TF IDF. So the number of documents where the token occurs, it can be used to calculate the inverse document frequency, because there, okay, again, there you have in the denominator the number of documents where the token occurs. So we already have this number. The size of the collection, this is just the shape of our data set. What about TF term? This is the number of term occurs in the document divided by the all length of this document. Where we can get these numbers, so I showed you the counter where we can easily obtain the number of term occurrences in the text, and the length of the text will be the length of the list of tokens. And actually, you have every information to complete this code. I will again wait for the answers in the chat.
By the way, Darina, there was a warning that you are not using GPU, but you connected the GPU. Whether there is any timeout when you got disconnected in if you just idle on the usage, if there is any penalty,
Is there
or
any
not using it, or it's just a warning which will reappear all the time.
Yeah, just warning.
So you are not like, if you just got the GPU not using it, it's okay.
Yeah. Yeah, I am feel a very bad person every time when I see this warning because I'm wasting the GPU of Google Earth. But yeah, actually, I could return to the normal.
It's not a green and sustainable NLP.
Yeah, yes, actually, yes. But I'm sure that we will use GPU in our next tasks. If for doc just an index of the row, what do you mean by index of the row? Document is, if we're talking about the data set again, document is this value from the column process review. So this is a document.
No, the question was about we have a tuple as an index or as a key. So doc
Yes,
and tokens. So
yes,
doc
yes,
is just an index.
yes, yes, exactly, yes.
Thank you.
So if okay, I will start with the loop. So this index, when you're iterating through the data set, is actually that index that you need to use. Oh yes, so the first answer for index doc in enumerate, yes. Yes, but okay, will be there any, will you continue your answer, or this is it? This is the final code for calculating TF-IDF. Because here, yes, you're iterating through the whole data set. You iterate through the tokens, and also you here obtain the number of occurrences from the counter. Okay, yes, is the key absolutely correct? But then you store only these values from the counter in the TF-IDF, and this is not the end. So I believe that everybody will successfully extract tokens from the text. So that was already as well in the answer. We will just iterate through the tokens. And what was written, but not actually fully in the answer, to calculate TF, we will use the number from the counter, yes. And divide it with the length of the whole document. But what do we need to do next? So yes, I can see the answer. Key and pair log. Yes, so now values divided by n and d divided by df of the token. Yes, what only can be the problem here, so when we wrote this function not just because we can, for the more comfortable usage, when, for example, you have when you will not have a token in the collection, for example, when you calculate your df, there can be an error that you do not have this token in the pre-calculated dictionary. So just to be sure that you will not have some error, it is better to use functions that we have already written that deal with this mistake. Okay, but actually, yes, so the logic is absolutely correct. As it was in the formula, we divide the length of the whole collection by the frequency of the token in the collection. So I will finish the code. So here you explicitly calculate it in your code, but I will use this function. And EDF will be calculated, yes, as NP log. Yes, the shape of the data set. Okay, so I will do it like this, divided by with a df. And now tf by df for the index token. Yeah, so yeah, I see. Yeah, so it wasn't double. Yeah, sorry for that. You just can write like this, the key. Yeah. But also what we can do more with this line. In classical formula that we saw, we just have log, but also we can use some smoothage for this and add here 1. And we will have a smoothed value of for the EDF. Okay. Just to check that we have the equal number of items in the dict. So for me, this is, you see the number 25,000. Is there any questions for the solution? And so I will leave maybe this in this way. And as we calculated the TF-ADF as the dict, so what, as you already see, the keys for this structure is the index of the document and the token itself. And we have this very, very long dict of 25,000 of elements. Maybe we can also look at some keys just to understand with which we are dealing. So we have here the index of document and the token. And the number, for example, here is just some TF-IDF. Okay, and but again, so this is a dict, and if we want to work with some matrices, so we want here to reproduce this dict into some very big, maybe sparse matrix, yes. And here's the code for this. And if we will look at this matrix, yes, it is. You can see a lot of zeros here and some rare numbers. of course, it's very sparse because if we write the whole vocabulary from the collection of document, there will be a lot of different tokens, and not every token represented in the document. And so the shape of this matrix is here. Here we have the number of tokens to the number of documents. So for the y-axis we have tokens, and for the x-axis we have documents. And when we will look at the product of this, so the number of elements, yes, actual elements in this matrix is quite big. And also I have some trick for you to look at the memory that is obtained with this variable. And in Python you can use such function as getSizeOf, and we will look at the dict firstly, and at the matrix. And of course the memory that is used with dict is less than with the matrix obtained, but again, this number is not so small. Yes, so the result is in bytes, and when we try to estimate, so this is 19 megabytes. This is not a very small number. And of course, that can illustrate that when we use some count-based models, and firstly, we need to deal with some sparse matrices again. So here are a lot of zeros, and here we obtain just some memory for zero numbers, and this is not very effective. And as a result, it can use a lot of memory, and will be not so optimal for your models for your further goals. Is there any questions for this?
Yeah, I think there was a question on the lecture as well, which kind of data structure to use to avoid this problem. And if you implement like this, probably you need to use something like sparse matrices, like compressed row sparse matrix. So yeah, that dense matrix representation would be the easiest way to implement it, but if you go for compressed sparse row or some similar data structure, the consumption of memory will be also proportional to dictionary or maybe less.
We will also have, for example, further. Yeah, so if there are any questions, we will finally use our obtained representation of tokens for the applications, for some applications. And as you remember, the initial task of this part was to find the most similar review for some query. And here we have we again need to write some function to calculate the similarity between the query and between the text in the collection. And the first implementation will be about will be based on TF IDF logic itself. So now we have TF EDF representation for the whole text in the collection, and we can use this information to calculate somehow the representation not only of the words but all the texts themselves. And so here you have again the functions that you need to complete. And what about the steps? First of all, of course, you need to preprocess your query here, and after that you need to calculate the similarity between this query and between the document from the collection. And that will be for this part, that will be just the sum of TF IDF of the tokens that both represented in the query and in the text. And after that, you will just have some sorted list and return top k results from the list. Again, I will wait for some answers, maybe not for so long this time. So the first step is quite easy for you already.
Maybe while we wait, we can make also some break because usually we make like a couple of breaks after like 1 hour of session, like 5 minutes.
Maybe we will complete this function, and after that we will have a break. Okay?
Yeah. Yeah.
And we can, so yes, so we will have for process query, and we can use our already written function per process for the query. And we will get the tokens of from our text. Yes, so here we will have we already have a structure to store our results, and so what should be done here? Will be there any guesses? So for me, the solution was we will go through the tokens that we have in the collection, and this information is basically stolen in the keys of obtained df idf dict. And if the token is represented in the query, then we will update the information inside our dict. And that's it. So we want to calculate the score for every document with respect to the query. And we just update this score with the TF or EDF of the keys, so of the tokens that can be found in the query and in the text. And that's it for this method. We and we can retrieve some results. I just took the first document for the collection, and we are trying to find some similar text to this query. And we want to look at the first 10 results. And so here they are. I believe that, I hope that you're still with me, and you're also successful in running this cell and what we have in here. So also this can be a problem, yes, because we extracted the query from the collection as well, and of course the more similar text to the query is the text as well. So on the other hand, that shows that our function works very good. Okay, it works correctly. I really wanted this work. It's a strange fit for me. The print is gorgeous. I believe that it's not a lot about the work and to tight in strange ways, love, colors, fabric. So you can see that the results are so, and maybe we can improve it somehow. And we will do it in our next exercise. And I believe that we will have some break for...
Yeah, let's have a break, maybe 5 minutes or something like this, and then continue afterwards.
Yeah, okay.
Okay.
I believe that we can continue. If anybody is here, please write some pluses. Also, if you have any questions, you can also ask them. If you have, maybe if you want to complete the code for the previous parts, I can show you for some time the answers. Can we norm the similarity? Talking about exactly this approach, I think that nothing will help it. But in the next step, we will look at some other solutions. Maybe that will give you an answer. So actually, yes, maybe if everybody is done with this and just want to know what is next, yes. So, okay, talking about other representation. Here we just use the sum of ways, just the sum of TF and EF. Of course, it is not the most representative way here to calculate the numerical representation of the text. This will be just some number, and this is all, sum just score. And of course, as we had here TF and EF matrix, and we can extract the vectors from this matrix to represent the text not with just one number, but with some vector. And here we will look, so the name of this part is cosine similarity. And what we will do here, we will calculate the vectors of the text, and after that we will calculate the scores with the cosine similarity between the vectors. Here we already have some predefined functions. So the first function is just the reminder of how can we calculate cosine similarity. And the next one is quite important here. So as it was said, we want to calculate, to obtain some vector. And for example, we again have some query. We have already divided this query in the tokens. And we also knew the predefined vocabulary from the collection, because unfortunately we cannot calculate TF and EF for the tokens that we do not have in the collection. And we also knew the number of documents in the collection. And what we are doing here, we want to calculate the vector, and the vector, this is as we saw in the previous, as we saw in the matrix D, where it was already calculated TF and EF for the all tokens with respect to the all documents in the collection. But why we just not use this matrix that was obtained before? Because we can have some random query, some text not from the collection, and this function exactly did the calculations for the documents that are not in the collection. And in this situation, we need to calculate firstly TF, because we do not know before what was the TF of each token in this document. And so what about the vector itself? It is again based on the tokens that we have in the vocabulary. So when we build the parallel between the obtained matrix D, so we have tokens and documents, and now we have just one document. And we recalculate TF, IDF for the tokens in this document. So if we will go line by line again, so we will have exactly the same as the same calculations that we had before. We calculate the number of occurrences of each token in the text, in this text, in the query. And we calculate TF. After that, we extract already predefined document frequency for the token and calculate EDF and save the TF IDF in the for the token that in the vector, and that's it. And now, based on these vectors, we want to calculate the similarity between the query and between the text in the collection. Again, maybe I will help you here right now to save the time. So the process step is the same as it was before. Where we just use the function for the preprocessing, and we obtain the tokens. So after that, in this case, we just use tokens to obtain the information about TF-IDF. Now we generate the vector for the query. Query vector, let it be. And use our predefined function. And here we put and df, yes, it is here in the function shape. So now we have the vector for our text, and we also, and as it was said, on the other hand, for the documents for the collection, we already have this matrix Z, and we can use it as the vector representations for the text. And now we calculate cosine similarity between this query vector and between the vector from matrix Z for the collection. After that, so here we have this code for sorting the list, and again we will return just top k results. Now, again, we will use just the first text from the data set, and let's look what will be the results. So will be better or not. So the query was, I really wanted this to work. It had a strange fit for me. The traps would not stay up. So the first, of course, we have the text itself. The print of this is gorgeous, the dress is beautiful, the title is strange. Okay, so the results also not so good. Okay, so here can be several points because again we use, so cosine similarity is intuitively should be better than just summing up the scores of the tokens. But on the other hand, we firstly use not the whole data set, but some subset of it, and maybe it cannot find very good text because, yes, you can see, so the cosine similarity between the text itself is 1. And after that, we had we had the big difference between the next most similar text. It is just 0.2. And this is not a very good result. Maybe in the collection there will be some better texts. Okay. Yeah, so if there are any questions? And so the question was here also about the memory and the time. Okay, maybe we can have some experiment if we use not just some subset, yes, of the text, but the whole data set. And we can try here to run the code for the whole data set. Yes, so preprocessing was quite quick, just df. Yes, it's also okay for it. Now, yes, you can see we have a bigger amount of keys. So this will be the same, this will be the same. And now TF-IDF, maybe also we can check the time of the calculations. And of course, it will be quite long. Not so long, not so long for Colab. And what about keys? Yes, it is quite big. But on the other hand, if we will try to make a query in this case, so let's see what will be about the time. Maybe I did not run some cells. No, it doesn't run. And actually, yes, maybe it was about the D. And now the shape of D is quite bigger. And also we can check the amount of memory that it obtained. So you can compare the numbers. It is very, very big in this case. Yes, and okay, let's try. Yes. Okay, for this time, let's look if it is good or not. Absolutely wonderful. This dress is wonderful, wonderful style. Wonderful in the pink. Very comfortable. So here we have the word comfortable. So we also can see the results with this word. Beautiful.
Yeah, I think the larger the collection you have, the more relevant documents also you will retrieve, because if you have just 0.5 relevance, it's still maybe not as relevant, but this just means there are no similar no enough similar documents. If you have like a more realistic information retrieval setting where you have like millions of documents or maybe hundreds of millions of documents, the chances are that you will actually find very, very similar document. But for this, of course, you will need to have larger background collection.
Yeah, so so again, in the collection we had 25,000 of documents, and the trick this time didn't work very representative for this collection. But again, yes, if you will have very large collections, so the time for the time of the finding some of retrieval or finding some similar document will be increased in times in comparison with this task. Okay, so we will go further, and also we will show you other tricks in which you can somehow improve the representativity of the vectors, again with TF-IDF. And for the first step, yes, we did our TF-IDF calculations with our hands, and this is very good for you guys. But in Python, you have already predefined methods to calculate TF-IDF vectors in sklearn as well. For example, the most popular library for the scientific calculations. And here you have the example of how you can calculate TF-IDF with this function just with several lines. And yes, so it works very quick, just some milliseconds. And what about the memory? So as you remember, we had this matrix Z that was of some millions of bytes. And here we have memory usage of just 56. And so what is the trick here? As it was said, and as you remember, I believe in matrix Z we had a lot of zeros, and Alexander mentioned that we can use sparse structures to save such matrices that had a lot of zeros in the structure. And so why it is better to use some predefined methods, some predefined structures, because when you calculated that with your own hands, you had not so optimal structure to save the information. And sklearn used a sparse structure to save this TF-IDF matrix, and of course it's very optimal in terms of memory. And after that, so we obtained this TF-IDF matrix. You already understand what it is about. And what we want to do next. Here is a reminder for you about SVD. And again, so even if we use some sparse structure, the real size of the matrix is quite big, and we want to compress it somehow. And for these purposes, SVD is very good. So what is the meaning of this decomposition? We have some matrix, and we decompose it into 3 matrices. That, and each matrix is less than the original one. And so we have these 3 matrices U, sigma, and V transpose. U and V are semi-unitary matrices, and the sigma is diagonal matrix with agent values of C. And in terms of our TF-IDF, in terms of documents and words, so we had this matrix of TF-IDF where we have in y-x we have words, and in x-x we have documents, and we decompose it into matrix U, which is words on some dimension. And so here we have again sigma with agent values, and we represent documents on some dimension. And we can use this vectors. So again, we can extract some vectors from these matrices and use it as a vector representation of the documents, of the tokens, and etc. Again, so this is one another approach how to get vector representation of the text from TF-IDF. And here the example of how we can use this SVD. We define the number of components. So in the matrix sigma, again, there can be also zeros. And on the diagonal, we have agent values and some agent values. So we have these agent values in decreasing order. And the most important values, which are the biggest numbers, bring the most information about the space. And we can ignore other not so big numbers. And in this case, again, we can reduce our dimensionality. So we define the number of components as 2. Just as an example, it can be any number. You can also make it more optimal if when you calculate the decomposition and just look at the most is the biggest numbers, and you can in this case define a more optimal number for the components. So for example, we will just use 2, and we decompose our TF-IDF matrix into these 3 matrices. And so yeah, okay, so we will get U sigma and 3. And as I also described to you, we can use them to extract term representations and document representations. And here, actually, I want to hear the answer from you to see if you understand what is going on here. It will be just some small task in this part. And I believe that you will be successful in completing it. So again, here we have matrix U and sigma. And again, so the dimensions of U are words by some dimension. And we extract only two, in this case, in our case, two most important components. So we not use every component from matrix sigma, but only first two components. And as well, so we want to multiply matrix U with matrix sigma. And in this case, we need to have correct dimensions, yes? So that means that we will take all the rows from the U and only first two columns of it. And here we will have only matrix 2 by 2. So just these most important components. And of course, for we have the symmetric situation. So will be there any guesses? Okay, I will not torture you for a very long time because we have actually a lot of stuff to do. Okay, so as it was said, we take all the columns of U and only first, all the rows of U and only first two columns, and multiply it with the first two important components from sigma. Okay, maybe that was a little bit tricky because actually we have S as the list, and we want to transform it into matrix with not empty diagonal, so diagonal matrix. And again, as it was said, we take only first k components. And here we have almost symmetrical situation. So what questions can be here? The first point that you should pay attention. So we have here we transpose, and so we yeah, if we're talking about we have the dimensions of documents by dimensions, but from the decomposition, we have transpose matrix, and it is dimensions by documents. And we calculate from the left matrix, diagonal matrix, and we calculate dimensions by dimensions, and we have a dimension by the documents. So to obtain the vectors for the documents, we need to transform this matrix. That's it. Oh, so okay. Yeah. And it also took us not so long time. What about maybe some curiosity about the memory to compare with previous results? So as we calculated decomposition, and now it is not a sparse matrix, we have quite big amount of memory than we had for TF-IDF. This is because of optimizations that already done in sklearn. And so now we have the reduced TF-IDF, and in comparison of with D matrix, it is lesser, not so much, but again, it is lesser, and anyway, it is some optimization. Now we can use this vector, so we have actually real representation for terms and documents, and we can use this information again to make some retrieval tasks. And again, so as we dealing with vectors, we again use cosine similarity. And here's the function as it was in previous example. So for some query, we calculate the vector manually. What we are doing here. So as we had...
Can you maybe also get the size of these terms rep and docs rep, just for comparison, like what was the original U and then the... Yeah.
So it is less. It is less than...
and for the documents...
and for the documents, okay.
Just, yeah, so it's basically several orders of magnitude less than use, which was basically containing all. Yeah. So
even
way less than.
Yeah. So when we compare, for example, with just TF-IDFs, it was in the first examples. So even this number is much less than it was before. So and for documents, so if we do not want to deal with words and just to obtain to store the representation for the documents already, so even is less than just for terms. In the final example, we will not use doc representations, but we will use terms vectors to obtain the vector for the query. And what is done here? So we again extract tokens from the query, and we calculate the mean of all the vectors for the tokens that are in the query. So if maybe you deal somehow with word rec, and also another trick is to calculate the representation for the phrase, is just to take the vectors for the whole words and just to calculate the mean for these vectors. And so I will run cells, and here we're again using cosine similarity. Let's look at the examples. I will remind you that here we're again dealing with the smaller data set with not the whole data set, because okay, so the results are not so good as we saw before, but I when I was preparing the seminar and I tried to run this TF-RDF and decomposition for the whole data set, it took a big amount of time. So it was 10-15 minutes. And so this is one of the disadvantages of this approach. So, okay, maybe we can deal somehow with the memory, but the time here can be not optimal at all. And again, so of course, about us disadvantages, unfortunately, you can see that, again, the results are not so good. And why is it? Another reason. When we calculating just some occurrences of the word in the text, unfortunately, that doesn't give us there any information about the meaning of the word. And we want to somehow to obtain it. We want, for example, to have some cluster of words that are actually similar to each other. And we want, in this case, to put the meaning in the numbers. And after this part with count-based models, we are going to the word-to-vec. Yes, so maybe if you have some questions, maybe we can try more components. Yes, of course we can try. Yes, of course we can run some experiments. And again, as it was said, it was just the example. Maybe yep, it's better. So if you try it and it is better, so this is very good. But on the other hand, when you increase the number of components, the memory that is used by these variables also increased. And so again, you can find this. You should find this trade-off. So again, you can use a whole matrix. You could use a reduced matrix. You could use some tricks from the SVD. But on the other hand, you will have this huge matrix that will will obtain a lot of memory, and maybe the result will be better. But you will need more time to calculate the vectors, more time to retrieve the documents, and yeah, maybe the results will be better, but again, time and memory will be not optimal in this case.
What's also important is to run it on a big collection, right? Because if you want to train this to compute a good decomposition, you need to have also not just a few documents, but as much document as you can, so that yeah, you can obtain more meaningful generalization over different words and categories. So it's even for two components, you might get much better result if you will calculate it for a much larger amount of documents.
Maybe any other questions? So we will go to the next part, to the word-to-vec. I believe that everybody already heard this term and heard a lot of time about what is it and what is the main idea, but I will give you a small reminder. So if we will talk just about not about some representation for our models in the future, but just about the words itself and how we understand the meaning of the word. And there is a very good phrase that we can understand the meaning of the words by its friends, so its context. Here we can see some example with some sentences, and here we use some very strange word, and when we read it for the first time, we cannot understand what it's about. But we here have several examples of its usage, And when we think about of the context and with about the words with which this strange word is used, we can finally understand that this strange word was about some kind of beverage made from corn. Yes, so we a bottle of everyone likes. So maybe this is very a good drink. Makes you drunk. So this is about alcohol, and we make out of corn. So now from this whole text, from these different contexts, we can understand the meaning of this word. And the idea of word-to-vec was based on this distributed semantics idea. So that we can understand again. So we can understand the word by its surrounding, about its context where it used. There are several implementations. Today we will talk about Skibram. Also, there is a SIBO. And okay, I will talk about all these terms after some minutes. But firstly, I advise you to run cells just to run, because here we have some additional downloading with the data set. So the purpose of this part is to train your own word-to-vec model. We will have explicit implementation of word-to-vec, and we will train our own model. For this, of course, we need a data set, and we need to download it for the collab. And also it will take some time, so I advise you just to run all the cells. And why it is downloading, I will tell you the theory, and we will go through the code. And also I advise you to run the cells in the Skibram model part. And yes, so just to run everything, and during this time I will tell you what is going on here. Yeah, so that was data set and some additional functions to propose this data set and to generate batches for our training part. I will not go through very thorough through these scripts, but if you look at it, if you have some questions, you can, of course, you can ask. Here you just need to check if everything is downloaded successfully. And so next, word-to-vec model. As it was said, we had here Skibram model example. The idea is that we want, so we create this task that we want to classify, we want to predict the context of the word by the word. Also, what about SIBO? So yes, we have SIBO is the reverse problem. So based on the context, we want to predict the word in the center, the word from this context. We will look here today here only on Skibram, but anyway. So what we also have here, we want to present our words as vectors. And what is it will be just some matrix of weights. So firstly, actually we have again this simple representation with one hot vector. So when we have all the data set, all the vocabulary, and we just put the sign that we had that we are working with this word, and after that we use the matrix of weights okay. We are dealing just with classical classification task, and we want to predict the words from the context. We want to classify the words from the context. So as a result, we want just to have output layer with probabilities that these words can be matched in the context of the given word. Again, this will be just some indexes. And as we work with some neural network, as we decided to take a neural network, we're dealing here with some weights. So this is just a simple structure of neural network. And we just want to train our model to deal with this task. Of course, if we're talking about our original usage of the words, we in our usual tasks do not want just to predict the context. As you can see, we want to retrieve some vectors to present our text and to do other more advanced tasks for our purposes. And what are vectors here? So we, after our model is trained, we can use these vectors from the layers. So these ways can be used actually as vectors for our watch representation. I believe that the idea is quite simple, and you already heard it on the lectures. And what should be reminded here as well? What about the objective? Again, so the task is we want to predict if we want to predict if what words can be used in the context of the given word. In the other words, when we have word you and word we want to calculate the probability of word we appeared in the context of word you. And it is written here. So for the whole vocabulary, for all words in our collection, we want to calculate the probability of appearance of the words in the context. So here we have the window, what we're looking at. So this maybe will be some +3, -3 words of the context. And we want to estimate the probability that we can use this word for the context with this word from the center. And here sigma theta is a parameter of our model. When we, so classical approach for the machine learning objectives, we here have multiplication of probabilities, but of course we want to write it in the sum, and we use for this logarithm, and we rewrite the same idea as the sum of logarithm of probabilities. And what we why here we have minus, because in the original idea we want to maximize the probability, because we want to ensure that these words are used, and this is for sure, we know this. But in the classical machine learning approaches, we do not work with maximization tasks. We are using minimization tasks. And here we have classical log likelihood loss function. Yeah, okay. If any questions, of course, you can ask. What about this probability? How it can be calculated? So this is just the softmax function, and yeah, it is written here. So this is the first part of this term, and okay, so the task is quite simple. We just have this normal network. We have this big matrices of weights, and we trying to use our loss function to find the optimal matrix of weights for our network. But what can be the problem here? Again, the problem always with the big data, when we have a very big amount of terms, of tokens, yeah, of vocabulary. What should be actually done in classical approach for the whole model? So we have this word, and we calculate all probabilities for all other words from the vocabulary. And when we make the optimization step, and we calculate the gradient, and we calculate the number on which every weight for every word should be changed. And in this case, we need to update the whole weights matrix. And okay, imagine, so we are dealing with some language. We're dealing with English, for example, or with Russian, and again, with English. And the amount of words can be very big. And imagine you need to update every time when you calculate the probability for every word in the language. Of course, it can be very long. So in the work, the authors used some tricks to optimize this step. And one of the tricks was the usage of negative examples. So what is about? It is about that we do not update every weight for every word. We do not obtain these numbers for every word in the vocabulary. We just randomly select the words that will be updated on each step. Of course, this number will be much less than the size of the whole vocabulary. And if we're talking about the exact numbers, it was calculated that for collections, not so big collections, the number can be just 20. For the big collections, it can be even 5 or 5, 6. So the number is much less than the whole vocabulary. And so this is the main idea. What is written here, and when we're talking about loss, so we concatenate these two losses for positive examples and for negative examples. Yes, and okay, so maybe any questions? I understand that you already heard it on the lectures. Maybe some ideas were not so clear, and we're talking about them right now. What about the implementation? So you can see that the skip-bram layer, yes, in terms of the lines of code is not so big. And we have these input embeddings and output embeddings, so the weights of the words that for which we predict the context, and the embeddings for the context. And we have here log sigmoid function as it was written here. So we calculate the log of probability, and we write is as a log of sigmoid. And in Torch, you already had this implementation for log sigmoid function. We had some initial installation of the layers, and that's it. So the forward step, we had these matrices U and V, and we calculate the probability of the words to be together in the context. So this is just the multiplication of two vectors. When you multiply here two vectors, you got a number, and you want to. So this is actually the probability of two words to be together in the context. And we had here the code for obtaining negative results. And so yeah, so if you ask me about the idea about how negative examples extracted from the collection, so the code for this is in these additional scripts. So as it was downloaded here, this is just very advanced randomization on the base of the collection. Actually, the whole idea is only about that. And again, we calculated log sigmoid for these negative examples, and returning the sum. So the loss is the sum of these two values. And actually, that's it. What about word-to-vec class? I won't go line by line, but so this is just the upper implementation of training procedure. We had the corpus. We defined here some additional variables, pre-process, pre-calculate also batches, and for every batch, we calculate the step of our skip-bram model. And also there is some additional functions to save the model, to load the model, to save the vectors, and also to find most similar, most important in this task, most similar vectors for some word. And I believe that the time was enough to download everything and also even to train our model. In further examples, you can just play with you already calculated, you already trained your own word-to-vec model. So this is the example of finding, to extracting the vectors. You can extract with some index or with the word. And also, as it was said, so there is a function for finding more similar words for the given one, and you can find. Yes, so wow, so very good model. Unfortunately, if we will take some more advanced examples, in this case, it will not work very good. So if, for example, we some word Python, it will not be so clever, unfortunately. But of course, okay, so what about the run? Here we should define the number of train steps as a skip window. So this is the size of the context which we're looking for the word. Also number of skips, this is the number of the words that we skip when we calculating the context. And also the number of negative examples. As it was said, we're not dealing with a collection from the Wikipedia or from the whole text for the English language. So this is just a small collection, and we can use here 20 negative examples. But unfortunately, the number of steps is not so big. You can try later bigger numbers. Maybe you also can parameterize these parameters and to find more better solutions. But as an example, here we have this model, and you can play with it. You can download. Here you also you have code for how preload already trained model, and also you can use it to do some algebraistic operations with the words, with the vectors. And here we have this famous example about king, man, and queen, and so how to, and some estimation of the similarity between these words. Okay, so maybe if you have any questions, you can ask, and I believe this is time to make a break again.
Yeah, let's make a small break, and please write also the question in the chat if you have some during the break, and we'll try to answer it. Yeah.
Actually, for everybody, I want to say that in the first parts, we will deal with some pre-trained models. And so just let me show you. So yeah, so here we have some model, and the size of this model is quite big, so we need to also pre-download it. And if you have any time, so actually you had time, and it is better to start downloading it now to not to waste 15 minutes later. Just an advice for everybody. Let's continue. If somebody is already here, please write some pluses if you're ready. Yeah. Okay, so we finished with our own model, and after you, I believe that you already fulfilled with the theory, and I have very great news for you that you can use already pre-trained models. You have already used already written implementations of the word2vec and not struggle with your own implementations. And so, yeah, again, we will look at some tasks at first. Just again, download the data set with, this is a core data set with questions from the Quora forum. And we will use it to, okay, for some exercises. Here again, you have some tasks for the preprocessing. If you want to deal with it, okay, so I will help you again. So the task was here to lower the text, after that to tokenize it and obtain the list of tokens. I believe that you have already fulfilled with processing as well. And so yeah, the solution is here. So we just use the we go through the sentence in the data, and for each sentence we lower it and tokenize it. And here we will have the list for all tokens. Okay, it will may take some time. And if you do everything correctly, you will successfully pass the source here. And just some example. Yeah, so as you can see, in this case, we didn't delete the punctuations, and we also didn't delete some stop words. As an example, that sometimes maybe you should leave these auxiliary words. Maybe it will help you, even help you for your task. And here we, one step before, we will use some already pre-trained models. This is an example of how we can use already predefined implementations. This is so one of the huge libraries for the already predefined and pre-trained models of word2vec is GenSim, and we can use models from this library, and we today will use word2vec. So this is just this is not already pre-trained model. This is just the class as we defined our own class. So here we have implementation from GenSim, and we will train this object with our data. Of course, it will take some time, but we will check if it works better or not than our trained model. Yeah. So here we have just some examples how we extract vector from this model. Also, we can find similar words for some given word. So let's look at the results. Here we have rice, fruit, cheese, honey, corn. So not so bad, actually. So this is quite interesting results. And again, we can try here the example with skin and man. The results are not so explainable maybe because again we have a very specific data set, we have just questions from the forums, and maybe there's not enough context for these words to build the connections between these two words. Yeah, but again, that was some build model based on the predefined implementation. And finally, we can use even already calculated vectors that actually done in the real life scenarios. We already had a lot of different pre-calculated vectors, vector models, vectors for the different languages. In this case, we will use globe representation based on the Wikipedia. You can go to the globe website, and actually here you will find that also for the globe there are several models based on the Wikipedia, based on the Chroma Crawl, and some of them are quite big. Today we will work with the smallest model because of the downloading and because of the time limits. And we also look at the results from these models. But of course, when you use even bigger models with based on the news, based on the corpus from the internet, it will give for sure very good connections between the meaning and the text. So I hope that you already downloaded the dataset, and now we not data you already download the vectors. And okay, so now we will use it. What don't you like?
Yeah, just to mention that this smallest model still was trained on like 6 billion of token corpus, so it's like small, but among others, like common crawl based one, but which uses like a big fraction of web to train, but it's still like not the kind of examples we smaller data collections we used in the previous parts of this tutorial. You usually want to have really like large and diverse and basically clean corpus to train. And this is why you usually want to use some pre-trained word embeddings, which were carefully trained on some large machine for a very long time. Project called Rus Victorious. They pre-trained a lot of models, and for English and other languages you will find as well many various models which you can just download like this. But of course, in some cases, you also need to train your own models if you have to deal with very specific domain or some other reasons, like words or language is not supported by the majority. But for your homework assignment, for instance, it would be relatively fine to just rely on such kind of models.
Yeah. So as you saw, not to forget to unzip the archive, and there you will have even several models. So yes, as Alexander said, the model was trained on 6 billion of tokens and of documents. And here also you have the models with different sizes of the vectors. So this is this part is about the dimension of the vector. And so here you have 100, 200, 350. We will take 300 dimensioned vectors and we will work with them. Yes, so here, as this is just the TXT file with some numbers not covered in some Python structure. So this to cells as an example for you how we can store these downloaded TXT files as some word-to-vec models. And again, we use here GenSim models, and keyword vectors is the class to work with different word-to-vec formats. Also here I have for you the code how you can download it in the other way. So you can download it right in the Word2Vec class with GSIM API. But unfortunately, as I tried before, now for Collab it takes a lot of time to download the model. So as you saw, it is not so quick process, but with API it can be even longer. But maybe with some connection it could work for you. Yes, so because this also takes some time.
It's usually better to save the model in the GenSim format, like with the save function, and then the loading of the model will be much faster because it just serializes Python object, and this function basically would need to read this entire text and then create all these vector structures, and this is why it actually takes quite a lot of time. But once you save it, then it will be much faster with a native GenSim functions.
Yeah. So almost 2 minutes it took, but okay, we will go further. And again, as in the previous examples, you can play here with different words and try to find connections between them. We also try this famous example for queen and woman, and you can see so somewhere king is almost magistrate, also on the first place as well. So coronation, not so bad, but also king, and maybe if we add as positive a man, and we will be lucky to see. Yes, so here is a king, and this is a quite good example to illustrate that we can sum and we can subtract vectors of words and actually obtain some meaningful results. Yeah, so also here are some jokeful examples. If we try to find some similar words for Python, it is funny that here we have Monty Python, as you know, this is very famous comedy group. But also here we have Perl, PHP as programming languages. I believe that the word Grail is here because we have Monty Python, and there is a movie with about Grail from them. JavaScript also about. So here we can see that as Python, the word as well has different meanings. We here have different results from different, how to say it, clusters from different spheres. This is can be some part of the name of the comedy group, but on the other hand, Python is a famous programming languages, and here we have examples of similar words to this one. If we're talking about PhD, very important topic for me. So this very representative example. So PhD, doctoral, doctorate, thesis, yes, of course, graduate before, postgraduate after that, and etc. But if, for example, we will have a PhD life and subtract from each panini, coffee, coach, experiments, paper, and others. Unfortunately, we will have some garbage examples. Yeah. So if to feel this joke, go to this link and maybe have a rest after the seminar. Yeah, so if you have any questions about the usage, about the model, about the idea. Also, another very good illustration of the this idea that actually we actually get the vectors that in which we will have similar words clustered all together, and of course we can visualize this, try to visualize this cluster, and we will do this right now. Again, so we just extract some first 1,000 words just to faster the calculations. Here also you have the small task, but I believe it is quite late to try to make you some exercises. So I will provide you with a solution. So yeah, so in this part of code, we just extract the word vectors from for the words. Yes, and some assert. And again, as we want to see some visualization, as you remembered, we are dealing with vectors that have 300 dimensions. And unfortunately, for now, at least we do not have such tools that will help us to visualize these 300 dimension vectors. And of course, we want to put it in 2-dimension and to build some graphs, some plot. So here we use again dimensionality reduction technique. Exactly for this example, principal component analysis. It is connected with SVD, but here we have centered metrics. So the idea as well, so we just extract we decompose our metrics into components and extract the most important components as we did before. And in this case, we will use already predefined functions from sklearn. And also here was some task for you, but I will help you quickly to deal with it. Yeah, so here we again we use 2 components because we want to plot in 2 dimensions. And yeah, so here now we have only vectors in only 2-dimension space. And let's draw it. We will check if we will have these clusters of words. Yeah, so actually, if we're talking about the whole amount of words, and as you remember, here we have not the whole vocabulary, but only 1,000. And yeah, so we can see very good divided clusters, but some connections we can see. So here we, on the left, we can see that these are all the numbers. Here we have a small cluster of, yeah, so everything is about the names of the months. And so this is quite good. Here maybe also some years. Even you can see, so this is just some numbers, and this is years. Also, this is numbers. This is months, and maybe that was about the dates. And of course, when we're talking about the text, of course, the dates when we have a date, month, and year, they are always together in the context, and that's why we have here some cluster of dates. Let's look about the right part, drew, feel things. So maybe it is about some personal feelings. and me, I, we. So here we have as nouns and some verbs about the feelings. What about some top examples? Cooperation, foreign, minister. So this is some government stuff. Yeah, so as a result, here we have maybe not so good illustration with very good separated classes, but anyway, when we deep inside the words, we can see that basically we have some structure here and really some words that appear together in the context and actually have some connected meanings, they cluster together. So very, very good. Yeah, cool. But in this part, it was only about phrases, but so it was only about words, sorry. But yes, the next step is to work somehow with the phrases, with the sentences, with the documents, because as we saw some examples, we, for example, have a task to find the most similar review, and this is a sentence, and we can work somehow with words, but we want to have this one representation for the text, for the whole text. And yeah, as it was done before, in this case, we again use this just simple implementation of calculating the mean of the whole vectors of the words that occur in the text. Okay, there was also a task for you. I will actually here give you some minutes if you want to complete it. I will wait for the answers in the chat because the task is quite simple. So here you have a phrase, you have a text, and you want to generate the vector for this phrase. You have to tokenize, to preprocess as well, so to lowercase, to tokenize, and after that, just to calculate the mean of the all vectors of the words. Or maybe you have some questions. So that will be some pause of 2 minutes for you. Okay, so I will hope that you are doing great, and my solution will not be a surprise for you. Explanation here. So, as it was said, we just lower the text. We tokenize it with our predefined tokenizer. Also, we will calculate the number of used words, but also you can use here some function from the NumPy. And so what we're doing, we just summing up the vectors for the words in the phrase, and then calculate the mean. Let's see how it worked for our example. And yeah, so we obtain here some vector for the phrase. And also, so we will try to visualize and to see. So also here was some small task for you. I will help you. Again, so we get the embeddings for the phrases from the data set. And again, we extract the most important components. And here we need just two because we want to have a plot on the two-dimensional space. And now we try to have some visualization. Okay, so now let's look if we are so lucky to have some clusters with phrases. So let's start with some right. Do you understand life and do you think you're beautiful? I believe this is some essential questions for how you should love yourself in 2020. Yeah, so let's look at the top. How can Spotify download sounds online, and how do buttercream cream ice and frosting separate? Okay, so maybe for the phrases we're not so lucky, but so how do the math guitar? Maybe math and guitar are also connected. I believe that everybody plays this game sometime. But so what can be the problem here? Yeah, the problem is that we use very simple approach of just summing up the all word vectors. And for the phrases, it's not so good representation in this case. We will try also not, we will also try here this representation for the task that we did in the first part of our seminar. As you remembered, we were dealing with reviews. And let's look, maybe these vectors of the phrases will be enough to do retrieval tasks. So yeah, so as you remember, we did it with DF IDF. This is exactly the same data set. Okay, so here we will use this phrase embedding function to calculate the factor for the query. And also, again, we will use cosine similarity to find the most similar phrases to the query. And so let's look at the results, if it is better or not. So again, I really wanted this to work. It has stretch for fit for me. Actually, it was about the fabric was beautiful, shoulders. Maybe this is actually about some part of clothing. The dress is adorable. I love the pattern. Horrible fit. Actually, strange fit, horrible fit. So here, you remember that in TF-RDF we had some very ambiguous results, and at least in the case of using a word to vec, even calculating just the mean of the vectors, somehow it is better connected to the meaning that it was with TF-RDF. Yes, another approach is to combine actually these two models, word to vec and TF-RDF. Because again, when I just calculate the mean of the vectors, maybe as in the case of TF-REF, yes, so we want to weight some more meaningful words more and to decrease the importance of some noise words. And again, in calculating not just mean, so we will calculate again the sum of the vectors of word-to-vec vectors, but in this case we will use this weight multiplication term to somehow increase the importance of some terms. And we will use this practical TF-REF that we did in the first part. And what is going on here? So again, now we're calculating TF-REF for the word, for the token in the phrase, and the approach as it was before. So we count the amount of occurrences of the word in the phrase and divide it with the length and multiply it with EDF of this word in the whole collection. So in this case, EDF is some approximation of frequency of importance of the word in the respect of the whole collection. Again, so we're talking about the some predefined collection, and that was collection of reviews. Maybe it is not so representative for the language, but you can improve this approach if you calculating maybe EDF not on the dataset of the reviews, but for example on some news, on some Wikidata, and etc. And now let's look at the results with this weighted word-to-vec with TF-REF. So actually, yes, both dress, it was perfect, horrible fit again. This dress can be casual. So actually, the results are somehow different. And here, not actually, no, not different, but also we talking about some dress, and we're talking about if you like it or not like, and etc. etc. So yeah, it is a little bit better, but of course there are more advanced approaches to calculate the vectors for the phrases, and it is called word-to-vec. I'm not sure if we will have time to talk about this today, but the idea is to train again some model based on the documents, not on the words, but on the documents as well. And maybe that will help to be more successful in the task of such retrieval. Yeah, maybe if you have any questions. So here we will talk about just some examples of the usage, but maybe you have a question about the ideas, about how can it be improved, and something like that.
Yeah, eventually for that kind of task, you want not just to look at these similarities, but also to have some form and benchmark. Usually, if it's a retrieval, you can have a collection of documents which are relevant to a given query, and then you can compute some metric. But still, when you design this kind of similarity functions, it makes sense to use this eyeballing approach just to look at the data, at the results, and if they are total nonsense, then for debugging purposes, it's still very useful. But to compare to good models, you already need some run-through data sets. I guess for the sake of time, maybe we should proceed to the next.
Yeah. Okay. Yeah, so first we'll have also some examples of how you can use word-to-vec representation for different tasks. So before it was retrieval, here you have some question answering engine. So actually in this idea of finding similar phrases in similar texts, you can even build some question answering engine with your again, so this is just some predefined functions. The example of the sentence here. Yeah, so we're dealing again with this Quora data set, and this is some question about how you can do something. Yeah, very interesting question actually here. Yeah, and now again we will use this function for calculating phrase embeddings based on word to vec. It will take some time to calculate it for the whole data set. And And again, here we will use cosine similarity. Here, what can you pay attention? So we used before similarity metrics from sklearn, but in this case, you should use. It is better to use to a distance from SkyPy because it is more optimal, and it is very useful to calculate the distance not between just two vectors, between two queries, but between the query and between actually two matrices, between in our case between the query and between the whole data set. So yeah, some optimization tricks. How do I enter the matrix? So we will believe so. How do I do a matrix transpose in Go? How do I live in the matrix? Also very important question. How I do the impossible? How do I enter? Okay. How does Trump? Yeah, it's also very actual questions for nowadays. Yeah, so you can see, so in this case, because we are dealing with task for which the data set was created, so we're trying to find some similar questions, and in this case, it works pretty good. So I believe that for the why don't I ask a question myself? Why I don't believe in myself? Yeah, so you should believe. Also. Yes, so here I talked about some optimization trick with this function from SkyPy. But again, when we're dealing with really big data sets, it can be also unoptimal to calculate the distance, to calculate the cosine similarity between the query and between the whole data set. And for more optimal solutions, you can check the FAIS library, which which can be used to more optimal storage of the vectors and for more optimal retrieval of the most similar vectors to the query. Yeah. Okay, so we will go, I believe, to our last part for today, and we did already several different tasks: retrieval, question answering engine, and for now we will build even a sound translation engine between a Ukrainian language and between Russian language. You can write for me if I'm curious that is there anybody from Ukraine or maybe from other countries and not from Russia. Yeah, so as you may know, that Ukrainian and Russian language are quite in some cases quite similar, in some cases quite different. Here you can see the examples, and you can try to estimate the connections between different Slavic languages. I don't know, maybe we can pick up some very funny example. No, I don't know. Yeah, so about the last word, palka and palitsa. Yeah, quite funny for Ukrainian language to have this word. Yeah, and again, we need to download some data sets with Ukrainian and Russian words, and actually it will take time. Yes. So, okay, maybe we will not run the whole code, but we will go through it. Yeah, so unfortunately, yes. So I forgot about this part about downloading. And what was the idea here? So actually we had these two spaces of word representations. We have Russian language and we have Ukrainian language, or any other actually different two languages. And what we want to do, we want to somehow transform one space to be fitted in another. And yeah, in terms of mathematics, how it can be written, it can be written that we want to apply some linear transformation on the space and to get another space. And when you look at this formulation one more time, you will notice that this is nothing else but linear regression task. And so the translation between two languages can be done just by training the model as a linear regression model. Yeah, and here also another trick can be applied. Again, for a more optimal storage, for more optimal solution, we can make a restriction on our matrix to be orthogonal, and again apply here SVD to obtain only the most important components, and use it as our representations. I believe that you will be very happy to play with it on your own if you're very interested in it, because unfortunately we cannot do it without data. And Alexander, I believe that this is maybe it for today.
You mean, okay, I think if we can extend it for some
minutes.
Bit more minutes. It's yeah, just to finish the example. It depends how much time we need.
Maybe some 10 minutes for downloading, because of course the next steps are quite quick, but this part with data is
okay. Yeah, maybe we can go through the code if something remains to explain, and then just run it quickly. So yeah.
Okay, so what about the code? Okay, I will fill for you the exercises, so for everything will be clear. So here, as it was said, we will have just some linear regression model to train to transform our space, and maybe I believe that we'll be lucky to see if it works for the real life words. Okay, so here will be the code for you just to check if your model is good enough. And yes. So here we will use all the knowledge that we obtained before about representations, about finding more similar vectors. And so yeah, and if you will look at the numbers about the results, yes, of your model. So actually, shaping is basically an August, and so the model will be good enough to find these two words very similar to each other. So some magic going on here. Also, yes, so when we talked about the SVD, yes, so we will look at the code as well. It is not so big. Yeah, so we just decompose the matrix and we use and we define transformation as a multiplication between u and v. So here just decomposition and multiplication, and here you can see that okay, for more similar words, as we remember that this word means August, so this is the name of the month. And if we're looking at the most similar words for this, so again, this is the names of the months, and it is also quite good. So what is going on here? We are trying to find the similar words from another language to the from Russian language to the Ukrainian language, and we are very successful in this. And if we look at the score, so again, the score review model should be quite good even for this task. And the last example was about training, translating not only word by word, but to get the translation of the whole text of the fairy tales. And yeah, so the code for this, you should just recognize the text. Also, maybe some other proposed thing about lowering and etc. And just find the most similar word from another language and just take the first examples of the most similar words between others. And if we look at the results, here we have some very short fairy tales and East translations. So if we look more precisely, it can be "Зробила собі, сделай себе", "Підвези, підвези". You can also notice this, maybe, yeah, sometimes for some words the translation is not so good, and as in this example, this is just the word itself, but for the others, the results are very, very good. And actually, this is very good translation from Russian to Ukrainian and vice versa. So again, yeah, this is a very bad example. So just some one letter word and some strange translation here. I will check if the downloading is already finished. Yeah, unfortunately, no. Yeah, but as we can see the results, it should work very good. And maybe then the last words about Dr. Vek. Yeah, so we talked before, so we saw the examples that sometimes, so the example of translation is quite successful, and but here we have already predefined somehow pre-collected data set to work very good. But when we looked at the visualizations and we looked at the retrieval task of the reviews, it worked not so good. And as it was said, the module of Dr. Beck maybe can be better for these tasks. The idea of this module is quite similar to the word Beck. So again, we dealing with these synthetic tasks as in Skibram or SIBO. Today, here you have like direct and again bow approaches. So we wanted to in the first approach, we want to predict the central words from the context based on this context. On the other approach, we want to predict the context based on the word. But in this case, we not dealing only with words, but we also dealing with the documents. And here in the first approach, so yes, it was context and we predicting the word, but context not only the window of the context in the text for the central word, but also the document itself. So we also adding this representation, this additional matrix for the documents. And on the other hand, we are predicting the context of some sentence. based on the document. So we are trying to predict if this sentence can be present in the document. So the idea is simple as it was in Word2Vec. And here I also had for you an example of how we can train our own Doc2Vec model. Also here we have some data preparations, some special data sets to train this model. Also we have here, again, this trick with positive and negative samples. And in GenSim library, we have already defined Doc2Vec model and also some additional classes to store the data set. And you can try to train your own model. So it was said we take here Doc2Vec model from the GenSim. And again, that will be the task for you as a home task, because you saw that for Word2Vec, sometimes it can take some time to train a very good model, and we try to do it today. And even for a small data set, it took some 5 minutes. But if we're talking about bigger data sets and bigger collections, and when talking about the documents, it will take you an hour to go through 3 iterations and to obtain some very good models. So it was only about some example of functions calling. And here you can see the example how you can train. So the iterations took me 20 minutes, 54 minutes. So the result was obtained only since the hour. So you can try by yourself, and maybe
maybe we can leave this as kind of a homework for to play with the Doc2Vec and some other models. But yes, the idea is that you can also learn in yet another way representations of documents. You can learn them with SVDs through LSA. You can learn them through TF-IDF. You can average with some weighting, but that's another way to do it. Yeah. All right. So yeah, maybe we can then
maybe somebody has a question.
Yeah. Let's see if there are questions from those who remain.
At least please signify if you're if there's
Yes, so there are still some
any
people
useful
alive.
information
That's
for
great.
you.
Yeah, it's long, but yeah, it's a very practical field. So yeah, there are a lot of things to cover, and I hope they will be all useful for you in solving some practical tasks. So wasted. So thanks, and yeah, tomorrow we probably will release the homework, and yeah, thank you, Darina.
About the notebook, I believe that we will just release the notebook with the solutions. It's not about that you have to complete. You will have the whole code. Just if you're curious about the last parts, you should run and you should play with the examples. This is not the part of some assignment.
Great. Thank you very much, and have a nice evening. Bye bye.